Alright, our last section in Calculus 1, it's a very important section, the fundamental theorem of calculus. As the name would suggest, this is really the theorem of which all of calculus hinges. It's the bridge between Calculus 1, differential calculus, and Calculus 2, which is mainly integral calculus. Let's go ahead and let f of x be a function. So we'll let y equals f of x be a function. Let's let it be a continuous function on some interval a to b. Now what we're going to do then is we're going to define a new function. We're going to define g, and it's going to be a function of x. It's going to be the integral from a to x of, well, instead of x here, we're going to use t. So we're just changing the variable. It doesn't matter that we change the variable for the function f of x to f of t. The integral is still going to be the same. So we have a function g of x. It's going to be the integral from a to x of f of t dt. Now, as you saw in your reading for this section, what that means essentially is if we've got points here a and b, and here's our continuous function y equals f of x defined on that interval from a to b and continuous. Well, what g of x is going to do, if you take some value x right here for some x between a and b, what does that mean? Well, that's the area under the curve from a to x. So what g of x gives you then is actually the area of some section of the graph. Now, what you can see then is that this is a function that depends completely on x. So this function here depends on x, which is why we wrote it as the function g of x. So if this x value changes, I can put this x anywhere I want within that range of the interval from a to b, and that area then is going to change. So if I move x over, the area is going to grow. If I move x back, the area is going to decrease. So the function changes, the area changes as we change x. So g is a function that depends on x. Now, let's just look at an example of that here. In this case, the function, instead of calling it g, we're calling it capital F of x. And capital F of x is going to be the integral from negative 2 to x of the function f of t dt. Now, f of t is this function up here. So what's going to happen here as we move along here, as x changes right now, the function has value 0 because the integral from negative 2 to negative 2, the area under that curve is going to be 0. Right now x is negative 2. But as x increases, let's just go for a little ways here. For example, now we have from negative 2 to, looks like about negative 0.75. And the area under this curve of f of x is equal to, it tells us about 0.442. That's the total area. Now as that x value increases, so this function f of x gets bigger, we're going from negative 2 to x, and this x is changing here on the right side. What's going to happen? Well, we're sweeping out more area underneath this function little f, and our net area should grow, which is the value of f of x. Let's just let it run all the way to the end here. And you can see our net area is continuing to grow as we're adding up this area as our x value moves along from under this curve. And so the function capital F of x, as you can see, is actually an increasing function. It's an increasing function precisely because the function little f was always above the x-axis, so we're always adding on positive area as our little x value moves along here. So it's an increasing function because the net area is continuing to grow. Now that's not always going to be the case. Let's take a look at another function. Here's a good one. Here we can see that the function f of x is sometimes below the x-axis and sometimes above. So we're actually going to have some positive area and some negative area being added in. Let's watch and see what happens with capital F, which again is the integral from negative 2 to x. So it's measuring the area under the curve as the x value moves along here. So here's some negative area, positive area, negative area, positive area, and finally some negative area. So now you can see that this is a decreasing function. It goes down as long as we were adding in negative area. Once we were starting adding in positive area, once little f was above the x-axis, our function started increasing. And it increased until we got to this point right here. Then we started adding in negative area, so the area of function started decreasing until we got to this point. At this point, you can see that the little f function is above the x-axis, so we're adding in positive area. So the big F function, the one that's adding up all the area, starts to increase again until we get to this point right here, which matches up with this point where the little f changes from positive to negative, so we're adding negative area now. The total net area is in fact 0 here, which tells us that big F ends up on the x-axis here, because this is a running total a running total of the total net area as x moves from -2 on out, -2 to +2. So we have just as much area below the x-axis in these blue areas as we do above the x-axis in these yellow areas. That's what that tells us. Okay, so with that in mind, then let's go ahead and look at that function again, g of x. So we have some function f of x defined from a to b, and we're going to say that g of x is going to be the integral from a to x of f of t dt. Now again, what that does is it sweeps out an area. Now if we look at the difference between g of x plus h minus g of x, well, let's suppose that this is x right here, and let's suppose we have this is x plus h. Now g of x plus h is going to be the area from under the curve from a to x plus h, while g of x is the area under the curve from a to x. So what that's going to give us basically is it's going to give us this area right here. Okay, so this is g of x to g of x plus h. Is that area right there. Okay, well, that's approximately equal to the area of this rectangle. We could think of as having a height of f of x, because remember that's what our function is here. F of x is the height of this rectangle, and a width here of h. And so you can see then that if we take the limit as h approaches 0 of g of x plus h minus g of x divided by h, well, that is equal to, that's the definition of the derivative of g. That's the definition of the derivative. Remember way back when we looked at the definition of the derivative as a limit definition. What's this going to be? Well, as you let this thing go down farther and farther, you're getting a smaller and smaller rectangle, and if you divide by the width, you're just left with the one dimension of f of x. And so when you take the derivative of this function right here, what you're left with actually is the original function f. F of t here, f of x here, it's the same function, we're just switching variables. Don't let that confuse you. In integration, the variable is just a dummy variable anyway, it doesn't really matter. Alright, so that's kind of something right there. Now let's kind of verify what we said with a nice simple example. Let's suppose that let's let g of x be the integral from, let's say, 2 to x of, oh, I don't know, how about x squared plus 3x dx. Alright, let's find g prime of x. Well, first thing we can do is integrate this. G of x is equal to x cubed over 3 plus 3x squared over 2. Actually, you know what? Let's change these variables here. I have x in there, but we want t. T squared plus 3t dt. So we have the variables here that we're integrating, t, and then we have this x variable up here. So now let's take this integration again. With our variable t, we get t cubed over 3 plus 3t squared over 2, evaluated from 2 to x. Well, when I put the x in, now I get the x cubed over 3 plus 3x squared over 2, and then when I put the 2 in, I get what? 2 cubed over 3 plus 3 times 2 squared over 2. Okay? Now, here's my function now, g of x. It's right here. So I can take the derivative of this. The derivative of the first term here is going to be, bring the 3 down, that divides with that 3, just gives me an x squared. Plus here the 2 comes down, divides, gives me just a 3x. Well, and then this is all a constant here. This is all a constant, so the derivative of that is 0. So I get g prime of x is x squared plus 3x, which is exactly equal to f of x, where f of t is t squared plus 3t, so f of x is x squared plus 3x. So the derivative of the integral here gave us back the function that we were integrating, and that's exactly what we're saying up here above. This, my friends, is the first part of the fundamental theorem of calculus. Let's state that, and then we'll look at some examples with that little piece of technology we're looking at earlier. What that first part of the fundamental theorem of calculus says that if we have a continuous function f on some interval a to b, and we define g of x to be the integral from a to x of f of t dt, then the derivative of that function, g prime of x, is in fact just f of x. That's all that's saying. So let's take a look then at what that means. Let's look at this visual again. Now here's the first function that we looked at. Remember that we have this function here. This is our little f. Big F is our, what we've been calling g in our notes. So big F is the integral from -2 to x. And we can see that that function just keeps a running total of the area under the curve here as the area gets swept out. Well, now what we've said is that the derivative of big F should give me back little f. So what we're going to do now is we're actually going to graph the derivative of big F, f prime, big F prime, and it should give me the exact same function as little f. Now how are we going to map out the derivative? Well, we're going to look at the slope of the line tangent as we move along this function big F here. And what you're going to see is, let's just start nice and slow here. Here we have a positive slope, so big F prime is positive. Notice that the slope's always going to be positive, so this function, well, that's not true. Yeah, the slope is always going to be positive, so this function f prime is always going to be above the x-axis. But as we move along here, the slope's increasing, so f prime is increasing. Looks like the slope is about as steep as it's going to get right here at 0. That would be an inflection point. We're going from concave up to concave down, so the second derivative is 0 here. So we are at maximum value at f prime, because f prime is just matching the slope. Now the slope is still increasing, but it's going down from what it was, so f prime is starting to come down, and as you can see, f prime is exactly the same thing as little f, and that's the fundamental theorem of calculus, that the derivative of the area function is in fact the original function itself. And we saw how that was when we did our g of x plus h minus g of x. Let's look at it for the other function that we did. Remember this function here, the area function actually gave us 0. There's as much area above the curve, above the x-axis, as there was below the x-axis. So now let's go ahead and look what happens if we do the derivative on top of this. Yes, you can see that we are getting the original function little f is the derivative of the area function big F. Pretty amazing stuff, isn't it? Pretty amazing. So, that's pretty much what this chapter entails. We will go ahead and state the second part of the fundamental theorem of calculus, which we've actually already looked at in 5.3. That's just the evaluation theorem. Second part of the fundamental theorem of calculus says if we take the integral from a to b of f of x dx, this definite integral, so this is a number, remember, it's going to be found by taking capital F of b minus capital F of a, where all we need is to make sure that big F prime is equal to little f. So that's the fundamental theorem of calculus. It just basically says that differentiation, integration, or inverse processes, which was not known coming in. We have two separate things here. One is finding rates of change, finding derivatives. The second was finding out about areas under curves, and it was not expected that these two things would be so interrelated, that they're inverse processes. But in fact, they are. So let's go ahead and look at some examples in the next video.